Welcome to the wonderful world of astronomy. This is chapter 2, Discovering the Universe for Yourself. And in this video, we're going to look at the moon. You can see in these two pictures, we have a crescent moon on the left and full moon on the right. So these are different phases of the moon that we see throughout every month. Our goals for learning in this video: why do we see phases of the moon and what causes eclipses? Lunar phases are the shapes that we see the moon. So as you saw in the opening picture, sometimes it's a thin crescent, sometimes it's a thicker crescent, sometimes we see the half moon or the full moon, and these are called phases of the moon. Lunar phases are a consequence of the moon's 27.3 day orbit around the Earth. So that's the first thing good to understand and remember, that the moon takes 27.3 days, so almost a month, to go around the Earth. Half of the moon is illuminated by the sun and half is dark. So this is important because we need to understand that when we see moonlight, the moon doesn't give off its own light. It's not a light bulb. It's not something that emits its own light. Stars, like the sun, emit light, but the moon only reflects the light that it receives, mostly from the sun. And so when you think about the sphere that is the moon, you have to understand that at any given moment, only half of it is getting sunlight. It's daytime on that half of the moon, and it's nighttime on the other half of the moon. We see a changing combination of the bright and dark faces as the moon orbits the Earth. So you look at this picture here, and here's the observer at the center, and you can picture, so she's there on Earth, and the moon is moving around the Earth once every 27.3 days. And so let's hold the moon right here as it's in direct line with the sun. So in all these pictures, the sun is up to off the screen to the top and to the left. And so the sun is illuminating this half of the moon. However, the observer doesn't see the lit half. The observer only sees the dark half. This is what's called a new moon. So you can't see the moon because the only part that's lit is facing away from the Earth. And so it shows a blue sky here because that's always going to be in the day. And in fact, it's going to be very close, almost in direct line with the sun itself. It doesn't have to be exactly in direct line, but it's in that general direction. So we go around a few days later. This will be about 3 or 4 days later. We have the crescent moon and waxing crescent. You can see that label down there under the picture. Waxing means it's getting bigger. Day to day, we see more and more of the lit part of the moon. So it's a crescent moon because we only see a thin sliver from the angle that we are relative between the moon and the sun and the Earth. We only see a thin sliver of the part that is lit by the sun. And if that's hard to comprehend at the moment, it'll become more obvious when we go as we take it around on its path. So let's keep going. The first quarter moon. So this is when there's a 90-degree angle. It's perpendicular between the moon, the Earth, I'll just call her head the Earth, the observers on Earth, and the sun. There's that 90-degree angle. And so we see half of what is lit by the sun. So we're actually seeing a quarter of the moon. It's called the first quarter moon. So we see half of the face that is showing towards us. We see half of the full moon, but it's called a first quarter moon. Really, we're only seeing a quarter of the moon, but it's more called quarter moon because it's a quarter of the way through the month. It's a quarter of the way through its cycle. And you notice the progression as it went from waxing crescent to first quarter moon, that the sliver of the moon is getting bigger and bigger. It's actually adding about 7% of its light with each day that goes by. So finally, not finally, but continuing on, it is continuing its waxing, it's getting bigger, and now it's not a crescent anymore. We see the majority of the face of the moon, and this is called a gibbous moon. So it's a waxing gibbous moon. And then we get 2 weeks roughly after the new moon, and it's the full moon. So let's look at this little picture of the moon. You can see the half of it that's lit by the sun. all of it is facing the observers on the Earth. So we see the entire face of the moon, and that's the full moon. You see, it rises at sunset and it sets at sunrise. When we are seeing the full face of the moon, it is fully across the sky from the sun. So you can think 180 degrees across the sky, that's where the moon is. So as the sun is rising, the full moon is setting. As the sun is setting, the full moon is rising. Contrast that with when we're over here at new moon, it rises and sets with the sun because it's directly or almost in line with the sun. All right, so in the course of these 2 weeks that have gone by, the face of the moon that we see is getting bigger and bigger. Well, it's gotten to its biggest, it's the full moon. And now it's going to start to get smaller and smaller. The right-hand side is going to start to disappear. And so we have a waning gibbous. Now, gibbous means it's more than 50% of the face of the moon that we normally see at full moon. But waning now means it's getting smaller. And as time goes on, now we're 3 weeks in, we're at the third quarter moon, and it's off 90 degrees from the sun, 90-degree angle from the moon to Earth to the sun. And so in the sky, it's going to look 90 degrees off from the sun. It rises at midnight. So when the sun is directly below our feet on the other side of the Earth, that's when the moon, the third quarter moon, is rising. It's at its highest at sunrise. So figure this 90-degree angle. If you point to the sun, you point at sunrise, and then you see this third quarter moon, it's straight roughly overhead, maybe not exactly overhead. That's a 90-degree angle there between your arms if you're using both arms to point, one at the moon and one at the sun. And then it'll set at noon. And it keeps getting smaller and smaller. Finally, it's a waning crescent, and that sliver gets smaller and smaller until it's a new moon again. And that's about a month throughout that whole cycle. The word month has its origins. It's related to the word for moon, by the way. So our concept of a month is based on the cycles of the moon. In chapter 3, we'll get more into this, how most every way that we count time, that we think about time, seasons, years, months, days, these are based on something astronomical. Again, we'll talk about that in chapter 3. So here we have just another picture, the same concept, although on this picture, imagine the sun is to the right off screen. So the sun is illuminating the same half of the moon at all times, but we on the Earth will see different parts of that lit half. You can see here's the new moon on the right, and we don't see any of the lit part. And the other extreme is the full moon. We see all of the lit part. And it goes around, and the moon gets bigger and bigger, and then smaller and smaller. You notice also what half of the moon is lit and what half is dark. When it's waxing, we see the right half. And when it's waning, we see the left half. And when you look at the sky, take note of the moon. When you see the moon in the sky, the lit half, or the lit part, I should say, is always facing towards the sun. Whatever direction the sun is, that's where the lit part is facing, because that's where it's getting its light from. So here it is, the phases of the moon. It's about a 1-month cycle. It's a 29.5 day cycle. Now, a little bit ago, I said that the moon goes around the Earth, and I didn't say 29.5 days, I said 27.3 days. And I just explained how the phases, the full cycle, has to do with the moon going around the Earth. So there seems to be a discrepancy here, but I'll get to this in just a little bit. The phases of the moon as we observe them on Earth are a bit longer than the moon's cycle around the Earth, 29.5 days. So think of it as about a month as it goes from noon or new moon to crescent to first quarter to gibbous, and that's the waxing phase. The moon is visible in the afternoon and evening. It gets fuller and rises later each day. Then after full moon, it's getting smaller and smaller. So the waning bit is the gibbous phase, the last quarter, otherwise known as the third quarter, and the crescent moon. So the moon is visible in late night or morning, and it gets less full and sets later each day. So let's look at a calendar. This particular calendar of the moon's phases is from June 2020. And you notice here it's getting bigger and bigger. And in this particular month, we had a full moon on the 5th. And so I know that about 29.5 days later, so about a month later in July, there's going to be another full moon, probably about the 4th or 5th. So it's getting smaller and smaller. It's waning gibbous. Here it says last quarter. That's also known as third quarter moon. The lit part gets smaller and smaller. Notice that the moon is still always there. Now, that may seem obvious, but oftentimes in artwork, when you see a crescent, you might see a star right there in the middle. It's still there, and interestingly, if we look at a crescent moon through a telescope or binoculars, we can see the circle here, the dark circle, and it's still got a little light in it, just very faint. And that's actually not sunlight, because we know it's not getting sunlight on that part, but it's rather Earth light. Earth is shining light, it's reflecting the sun's light onto the moon. Just like we get moonlight, the moon gets Earth light. So if you get an opportunity to look at a crescent moon through binoculars or telescope especially, you can make out that the rest of the circle very dimly. It's getting what's called Earth shine. It's a thin crescent, smaller and smaller. So here we are, a new moon about 2 weeks after the full moon. And then the crescent reappears the next day, bigger and bigger and bigger. Then we have the first quarter moon getting bigger. Now it's waxing, getting bigger. That's the end of the month. So we're at a waxing gibbous on the 30th. And it's going to be probably about 5 more days or so before we get to a full moon. So on the next page, I'm going to get to the July calendar. And so there's the June calendar squished up at the top that I was just showing you, and it continues to get bigger and bigger. And there we are on the 5th of July, a full moon. And you notice between any corresponding phases, it's about a month's difference. So the third quarter moon or last quarter moon was on the 13th of June, 29.5 days later. So on the 12th, there it is, of July. The new moon was on the 21st, and so you can expect that about the 20th of the month, of the next month, there's going to be a new moon, and there it is. First quarter moon, you can see the 28th of June, and then the 27th. An interesting feature of the moon is we only ever see one side of the moon. The moon is rotating, and it's going around us, and so if it's rotating, we should be able to see all the sides of the moon, but a curious thing about the moon is that it's in what's called synchronous rotation around the Earth. Because it is of a size, it's much smaller or lower mass than the Earth, but it is of comparable mass. And so this sometimes happens when two things, planetary objects or astronomical objects, are of comparable mass and in orbit around each other. One or both of them gets locked into a synchronous rotation, which means in this case, the moon rotates exactly once every time it orbits the Earth. So it's spinning at exactly the same rate that it's moving around the Earth. So if you figure, here's the Earth right in the middle, the observer, and this person is pretending to be the moon, and this person is going to spin around on her axis at the same rate that she moves around the Earth. So she's pretending to be the moon. She goes around 90 degrees, and figure that's 1 week of the moon's travel. And she has spun 90 degrees. She was facing to the left, now she's facing towards the bottom of the page. And she keeps on spinning at the same rate that she's turning. So she goes around, by the time she's gone all the way around, she's spun around 360 degrees. She has also orbited around the model of the Earth, 360 degrees. You notice that all the way around, her same front as opposed to her back or her sides. Her same face is facing the Earth. So from the Earth's perspective, the Earth never saw her back because she was turning at the same rate that she went around. So that's what the moon is doing. It rotates and it orbits in 27.3 days. I said before in this video that the moon orbits around the sun in 27.3 days. Then I explained how it's the moon's rotation or revolution about the Earth, its orbit around the Earth, that causes the phases of the moon. So one orbit around the Earth goes through the cycle of all its phases. And then I said, but the moon's phase period is not 27.3 days. It's a little more. It's 29.5 days. So I want to explain that discrepancy now. The full moon is, as you can see this lineup right here, you've got the sun, the earth, and the moon perfectly in line. Now I want to imagine the moon goes around the earth. It's going to take about 1 month to go around, 27.3 days. Let's advance this slide 27.3 days and then see where's the earth and where's the moon. Okay, so while the moon has made one complete orbit around the Earth, so now it's exactly to the right, you notice the Earth has moved as well. The Earth has moved, and so the moon, so if you look at this top picture, the moon is no longer in the condition of having a full moon. It needs to be in line with the sun and the Earth. So the moon has a little bit of catching up to do. 27.3 days have passed, but the moon has to catch up to get up to where my red pointer is right here. And so that's going to take a little over 2 days. And then it's going to be a full moon. So that's why the moon phase period, just a few more days, about 2.2 days more than the moon's orbital period. Throughout chapter 2, I'm talking about different astronomical phenomena that we see on Earth and the explanation for them. And in ancient times, people made a very big deal about strange things that they saw up in space, what the planets were doing, what the moon, what the sun was doing, and often they attributed them to the actions of deities that were up there in the heavens. And sometimes some scary things happen, such as an eclipse. And eclipses have been, at least one eclipse in ancient times was known to have stopped a war that had been going on in 5 years around the Mediterranean area. And kings and emperors were very concerned about having astronomers who could predict eclipses because they thought what was going on in the heavens had something to do with how they should be ruling their empires and their kingdoms. And one very scary event was an eclipse, either a solar eclipse or a lunar eclipse. Now, first thing to understand is that the Earth and the Moon cast shadows. So in this case, what you see here is the Earth moves in the way, blocking the sunlight from getting to the Moon, you're going to see a decrease in light from the moon. And remember, the moon only reflects back to us the sun light that it receives. So when either passes through the other's shadow, we have an eclipse. What you don't see in this picture is a solar eclipse. So watch my red pointer, which is at the moon. When the moon is on this side, blocking sunlight from getting to the Earth, you have a solar eclipse. So there are two kinds of eclipses I want to talk about now, a solar eclipse and a lunar eclipse. Let's talk about a lunar eclipse first. Lunar eclipse, the word lunar eclipse, it refers to the thing that is being blocked. So a lunar eclipse means the moon is somehow being blocked, and a solar eclipse means that the sun is somehow being blocked. So with a lunar eclipse, you have the sun, the moon, and the earth. The sun, the earth, and the moon has come into the shadow of the earth. This is what's called a total lunar eclipse, when there is no sunlight getting to the moon, or actually very minimal sunlight. You can see it's in the shadow. It's through what's called the umbra, which is the deepest part of the shadow of the sun. And what we get there is a very dim red moon. It's red because it's getting a little bit of light that is passing through the Earth's atmosphere, skimming through the Earth's atmosphere, and a little bit getting to the moon, but not much. So it's a very dim red moon. We can also have a partial lunar eclipse. So if the moon is not completely in the deepest part of the shadow in the umbra, it's in what's called the penumbra partially. So the penumbra, which is almost the umbra, almost the shadow, is where it's getting a little bit of sunlight, but it's partially in the umbra. So we're not going to get that red. It's going to look kind of like a crescent moon. And then we have a penumbral lunar eclipse, which is when it's getting sunlight, but just having a little bit of the light blocked to it. It's in the partial shadow. And so what we see is it's the full moon, but not quite as bright as usual. And by the way, all of these occur during a full moon. Lunar eclipse has to happen during a full moon because remember back when I was showing you the phases of the moon earlier in this video, the setup for full moon is sun, earth, and moon. So when can eclipses occur? Lunar eclipses can occur only at the full moon. Lunar eclipses can be penumbral, which is this lower one here, partial, or the prettiest kind is a total lunar eclipse. Now there's also solar eclipses. A solar eclipse is when sunlight is being blocked by the moon. The setup is always going to be during a new moon, so we have the sun, the moon, and the earth in direct line. Solar eclipses can be partial, total, or annular. And let's look down at this picture below. This photo from Earth orbit shows the moon's shadow, its umbra, on Earth during a total solar eclipse. Notice that only a small region of Earth experiences totality at any one time. And this is one big difference between solar and lunar eclipse. When there's a lunar eclipse, when the moon is in the shadow of the Earth, all of the moon is being eclipsed. During a solar eclipse, it only affects some people on Earth. And so you can see this shadow in the umbra. Total solar eclipse, let's look at this picture on the left. The moon is blocking the light to the sun. And in that little region right there, you get the total solar eclipse. A partial solar eclipse occurs in the lighter area surrounding the area of totality. So it's in the penumbra of the sun. And most people who get an eclipse are in the path not of totality, but of the partial, where they get maybe, you can look at this picture here, where maybe 60% or 70% of it is being blocked. And the closer you are to the totality, the path of totality, the more of the sun is going to get blocked. And then one special condition is called an annular solar eclipse. This is when the moon is a little closer to the Earth than it usually is. So it looks, a little farther from the Earth than it usually is. And so it looks a little smaller in the sky compared to the sun, and you're going to get that ring. So it's almost a total solar eclipse. It's got the makings of a total solar eclipse, but the moon is a little farther away, and so it's covering up a little less of the sun. This picture is of our courtyard area between buildings at the college. This was in 2017, August of 2017, a very hot day, of course, as August tends to be in Porterville. But while the sun was up, while we were having a solar eclipse, it was pleasantly cool for about an hour and a half. And there's the college's telescope set up, and good time. People have various equipment to look at the sun, and there's someone with a cardboard viewer right there. And the telescope, notice it actually has a solar filter on it, so we could look safely at the sun. And somewhere in that crowd, with the cardboard viewer. This is something that a former student of mine actually brought. It's binoculars on a tripod. One of the eyepieces is covered, so it's acting like a telescope and projecting the sun onto this piece of paper. So we had about 70% coverage of the sun. You can also, if you look at the sunlight during an eclipse through a colander or just punch little holes into a sheet of paper, you can see the slivers. You can also see sometimes the sunlight coming through trees. The shadows are little slivers of light. So here's an example. This is up against the wall of the science building. We have notice all these little slivers. This is actually the sunlight coming through little gaps between leaves in the trees. There's a photo of a very partial solar eclipse. So if a solar eclipse happens during a new moon, remember the phase of the moon, you have the sun, the moon, and the Earth in line for a new moon. And the question is, why don't we have an eclipse at every new moon and every full moon? So a solar eclipse at every new moon and a lunar eclipse at every full moon. And the reason is that as I drew the picture of the phase of the moon on a two-dimensional surface, the screen you're looking at, it looked like during a new moon, the sun, the moon, and the Earth were in direct line. But there's a three-dimensional component to it. The moon's orbit is tilted 5 degrees to the ecliptic plane. And so the sunlight on this picture is off to the left. There's the sun coming on, and it depends whether the moon is up or down a bit. So in this example, the moon is up high here, and it's getting plenty of sunlight, so it might not be eclipsed. And also on the other side, 2 weeks earlier, or 2 weeks before, if the moon is down low sufficiently, then it's not going to be blocking any of the sunlight to the sun. It's only when this tilt is such that the moon is right here. So for example, let's say the moon were right where my red pointer is, and the sun happened to be pointing in that direction. So off screen, slightly, basically, if you're looking at this properly, over your right shoulder. Then that would be the makings of a solar eclipse. So we have about 2 eclipse seasons each year, with a lunar eclipse at new moon and solar eclipse at full moon. So about twice a year, that means somewhere on the Earth, probably not where you are, but somewhere on the Earth, twice a year, there is a solar eclipse. And then either 2 weeks prior or 2 weeks after, there's going to be a lunar eclipse, as the moon is in the full moon phase. Now, the path of solar eclipse, the path of that totality, the shadow, is so thin that, as I said, it's probably not happening where you are, but it is somewhere on the Earth. So a lot of people travel great distances to the other side of the Earth to see a solar eclipse. Some people are content to just wait until one comes to them. I haven't done the calculation, but I've been told that if you just wait in the same place on Earth, you're guaranteed to get a solar eclipse, a total solar eclipse, about every 320 years. Here's another diagram showing a setup for a lunar eclipse. You've got the sun, the moon, and this is an extreme, an exaggeration of the tilt of the moon. Remember I said it's only tilted at 5 degrees to the ecliptic plane. This has it drawn at more like close to 40 degrees. But just to embellish this, so you can see that sometimes the moon is directly in line, but sometimes it's tilted up a bit for that partial lunar eclipse. Sometimes it's tilted up a bit more for no lunar eclipse. In summary, 2 conditions must be met to have an eclipse. One, it must be a full moon for a lunar eclipse, or a new moon for a solar eclipse. And I don't want that to be a sentence that you just simply memorize, but rather I want you to think conceptually why that's true. So I do want you to remember the phases of the moon, how the full moon is when you have the sun then the Earth, then the Moon, and we're getting all of the light, all of the lit portion of the Moon, it's all facing towards the Sun. That's a full moon. And that's the necessary setup for a lunar eclipse when the Earth is blocking the light to the Moon. And then the new moon, that's the setup where there was the Sun and then the Moon and then the Earth. And that's what you need for a solar eclipse. So that's the first condition that must be met. Second condition is the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane. That's actually called its nodes. You don't have to know that word for this class, but the tilt has to be right so that it actually crosses in line between the sun and the Earth. Predicting eclipses. We can predict eclipses years and years and actually probably centuries out because the Earth and the Moon move in predictable orbits. And this chart is a little outdated, but it just shows different eclipses that are coming up. Some of them have passed. Here are the most 2 recent ones as of when I'm making this video in 2024. So we had one in October 2023, October 14th, and we got to see some of that in Porterville. And then April 8th, 2024, one crossed through North America. And the projecting on this particular map don't show anymore in North America. I think there's one not coming through North America again, I think for about 20 years, something like the year 2044. But you can see all around other solar eclipses predicted, such as January 2028 going through South America, February 2027 through South America as well, and through Africa, and you can see all these different ones. So if you want to go to see a solar eclipse, you can use a chart like this to make your travel plans. The thin band is just the path of totality. So let's look at the blue band for April 8th, 2024, where my marker is going. People who were in this line, they experienced the total solar eclipse. The farther up you go, or the farther away from that line you go, the less totality you're going to see. So we're in Porterville right here, and I think we saw about 40%. So I think pretty much everybody in the United States, not Alaska, I'm not sure what Hawaii got, but they experienced some kind of total solar eclipse. So you don't have to go exactly to where the band of totality is, but I figure if you're going to travel hundreds or thousands of miles, you might as well go and see the total solar eclipse. So in this video, what have we learned? Why do we see phases of the moon? Half the moon is lit by the sun, half is in shadow, and its appearance to us is determined by the relative positions of sun, moon, and Earth. And what causes eclipses? A lunar eclipse is the condition where the Earth's shadow is on the moon. A solar eclipse is the condition where the moon's shadow is on the Earth. And the tilt of the moon's orbit means eclipses occur during 2 periods each year. And that is all for our study of the moon. Have a great day.